Hello and welcome to a Reigate Maths video. This video is focusing on the root inspection section from the first year of the Decision 1 unit from the Edexcel Further Maths specification. My name is Simon and this video is going to cover the root inspection problem and the algorithms we need to use in which to solve it. The root inspection topic does come up very briefly in the second year, but it uses exactly the same ideas, but a little bit on top. So let's have a look. First off, the problem. What we want to do is traverse a network using every arc and return to the start point in the shortest possible length. Ideally, you want to use every arc exactly once, because that is going to give us the shortest possible length, but that might not be feasible. There are two key definitions that we need to think about for this problem. That is looking at an Eulerian graph and a semi-Eulerian graph. An Eulerian graph is one in which every vertex has even order. If that is the case, then we are able to traverse a network using every arc exactly once and then return to the start. A semi-Eulerian graph has exactly two odd vertices. If we try and traverse a network using every arc exactly once, if we start at one of the odd vertices, we will end up at the other one. So the length of the shortest route in that case, we're going to need to go back from one odd vertex to the other one. So the length of the shortest route is going to be the sum of all of the weights of the network plus the shortest path between the two odd vertices. If a graph is neither Eulerian nor semi-Eulerian, then that means it has more than two odd vertices. Remember from previous videos, a graph must have an even number of odd vertices. And in that case, we have to use an algorithm to find the shortest possible route to traverse a network using every arc once and then return to the start. In the second year, this is done with more than 4 odd vertices. So in this video, we are just covering what we do if there are 4 odd vertices using the Chinese postman algorithm. The second year is usually if there's 6 odd vertices, but they put constraints on that, and we've got a separate video to cover that case. So let's get into this additional case, this having to use what's called the Chinese postman algorithm. So we've got our network here, and we want to find a route that starts at A, traverses every arc in the network, and then returns to A. We're going to find the possible route and state its length. So we're going to apply the Chinese postman algorithm, because we can see that there are more than 2 odd vertices. We've got an odd vertex here, 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 and here. Just a reminder, the order of the vertices are the number of arcs that are incident to the vertex. You can see underneath the network, we're given the weight. That is very, very typical. The total length of the network is fundamental to finding the length of the shortest route. They're not going to make you just mindlessly calculate the total weight itself, so they just give it to us. So because there are more than 2 odd vertices, the first thing we have to do is list the odd vertices. And that is just as simple as writing them down. C, D, E, and F. Now what we're going to be doing is deciding which paths we need to repeat in order to be able to start at A and finish at A. The routes that we repeat are going to be the routes that link these odd vertices together. So what we need to do is we need to think about all the possible pairings. So if we pair C with D, then we have E with F. So what this means is if we are choosing this set, we are going to repeat the shortest path from C to D, and we're going to repeat the shortest path from E to F. By repeating these paths, we make the odd vertices even, and therefore we will have no odd vertices remaining in our network, which thus allows us to start and finish at the same point. So this is one of the pairings. We could have C paired with E, and in that case D has to pair with F. And then finally C pairing with F means that D has to pair with E. So we've got 3 pairings, each with 2 groups. If we had more odd vertices, we would have more pairings. So the first thing we do is we list the odd vertices, and then we write down the pairings. With 4 odd vertices, there will always be 3 pairs, or 3 pairings, made up of 2 pairs. What we're now going to do is find the shortest route from C to D. And by shortest, it's shortest length, not fewest number of arcs. So sometimes you do have to be careful and look very closely at the network to see which one is the shortest route. So we can go C directly to D, which has a length of 250, or we can go C to G and then G to D, which has a length of 200. We could go C to G, then G to E, then E to D, but that's 250, that's not shorter. So you do need to be careful. Now you don't need to, but I like to write down the actual path that we take, because it's going to potentially help us later on. Because the question says find a possible route, we need to work out the route anyway and write down a long route, so it just helps us a little bit. So we can see that's 200. E to F is just E to F. All of the other routes are much, much longer. So E to F is just 150. And then what we're going to do is add them together, and that is the sum for this pairing. We repeat the process for the other pairs. So we've got C to E. We can go C to G, G to E. It's going to be shorter than any of the others, which again is going to be 200. And then D to F is D to E, and then E to F, which is also 200. This last pairing we do have to be a little bit careful. C to F, because we've been doing everything else so far down at the sort of bottom of the graph, it's very easy to think, oh, C to F, I'm going to go sort of this way, C to G, G to E, E to F. But if you look, that's 350. We can go C to B, B to A to F, slightly shorter. So you do need to pick the shortest one, so be careful. That's what I was saying at the start of this algorithm. You do need to be very careful to check for the shortest one. We can see 325. D to E is just D to E, so that's 50. So we get 375. In the grand scheme of this example, getting this one wrong by going C, G, E, F and getting 350 isn't going to affect your final answer. So in terms of the exam, you're likely not to lose many marks for that error, but it's better to not make the error at all. If it does happen that by making that error we got a shorter route here than 350, you'd still get the mark for choosing your shortest one, you just wouldn't get your final mark as well. Once we've got our pairings, we just need to work out the length of the optimal route. We can see we're going to use this one because this is the shortest option. So the length of the optimal route is going to be 1,500 plus 350, which is 1,850. What's very useful to do is also to write down which arcs you are repeating. Or at least the route that you're repeating. C to D and E to F. So we've stated the length of the route, we need to find the route. To find the route, what you might want to do is draw these repeated arcs onto the network that you are given. So we're repeating C to G, and then G to D, and E to F. So you can see that C, D, E, and F, the odd vertices, have now become even with these added arcs. Now we just need to find a route that starts at A, finishes at A, that uses all of these arcs. It doesn't matter. What I tend to try to do is use these repeated arcs one after the other. So I'm going to go A to B, B to C, then G to C straight away. So it means I don't have to worry about them again. Then I'm going to go to D and do the same thing. And now we need to be careful. It's not as simple as just going, oh, I'm just going to whiz round, go around the edge, and then deal with the middle. We've got to make sure we go over every arc. If you're finding it difficult and finding you're losing track, tick them off as you go. So we've done A to B, B to C, C to G, G to C. Then we've gone to D, done the other two, and then we've gone to E. We can see we're going to need to go to F, and then back again. So we're here. Go through G to B, then to F, and then to A. There are lots of possible correct answers for this route. This is not the only one. So just because you might have one that's different to what it says in a mark scheme or what it says in an answer doesn't necessarily mean yours is wrong. You should double check yours, make sure you've hit every arc. And if you have, and you've started and finished at the same point, you've done it right. Now, other things to note that you might get asked is the number of visits. So I'm going to use G as the example here. Now, obviously, we can just count the number of times G appears in our route. But we can be a bit more consistent, a bit cleverer with it if we're not asked to find the route itself. So a visit constitutes entering a vertex and leaving. So uses up 2 arcs. The order of G is 6 with the repeated arcs that we're using. So therefore, the number of visits is the order divided by 2, which is 3. And we can see that G appears 3 times in our route. The only vertex where this doesn't work is the one that you start at. So we can see the order of A is 2, but A appears twice in our route because we started and finished there. So that's something to pay attention to. Now, because this algorithm requires you to find the shortest route between sets of vertices, quite often what they will do is use Dijkstra's algorithm as part A, where the starting point of the Dijkstra's algorithm is one of your odd vertices. And then we'll use this algorithm as part B, where you have to use your answer to part A. Other than that, there's not really much more to route inspection. As I said, in the second year, this idea extends a little bit to see what happens if you have more than 4 odd vertices, but we put restrictions on that so you're not having to do this method fully with 6 odd vertices, because at that point it's just doing the same thing but more of it. Incidentally, the number of pairings you have for 6 odd vertices is 15 pairings, each with 3 pairs of arcs or 3 pairs of vertices in. So it's lots to do that doesn't actually test anymore. So don't panic and think, oh, I'm going to have to do this fully with 6 odd vertices. The second year, it changes it slightly, but it's basically just doing this again with a little bit of extension. But that's the route inspection problem. It's one of the shorter topics in the decision unit, which is quite nice. And if you can follow the algorithm, much like a lot of the other topics, it's relatively easy to do. Thank you for watching.